Welcome back. This week we look at springs. Now, a spring, certainly in the mechanical engineering context, is normally one that looks like this. Obviously you get leaf springs as well, but this is now a close coiled helical spring. Now, as you can see, the close coiled helical spring is made up of a suitable wire that has been rolled into a helical shape. There is a view of a spring, and there's another view of the same spring. And as you can see, out of interest, the ends of this particular spring are ground flat so that it suits the machine that it's being used in well, but other springs might not be ground flat like that. Now we need to consider a few terms that are used often. The first is free length. Now here you'll see the spring which has been put between the two jaws of a vernier, and it's currently measuring 54.79 millimeters, and that is when it's in the free condition. In other words, there's no load being applied to the spring. This vernier is very lightly touching the ground edges of the spring and measuring that in its free condition with zero load in the spring, it's measuring 54.79 millimeters. That would be known as the free length. Now here the same spring has been put in a vise, and the vise has been wound closed somewhat to an arbitrary length of 41.08 millimeters. So that would be the spring which is compressed to a new length. Now clearly inside that spring there is load because the vise is holding a force against the two faces of the spring, making it shorter than it was. You can see this number is less than the free length, and there is some load in that spring. And then lastly, here is that spring at what is known as solid length. The vise has been wound as tightly as it can be, and the spring wires are now touching each other, and we now no longer have a spring, we now have a solid item basically that cannot get any shorter. The vise has now reached 31.79 millimeters between the two jaws. The spring wires have touched each other, and we've now reached solid length. We now no longer have a spring effectively, we have a solid object. That is called solid length, which for this particular spring is 31.79 millimeters. Now, to analyze what's going on in the spring when it is under load, let's go in and consider one of the coils, one of the turns of the coil rather, and let's cut it, obviously an imaginary cut over there, and just consider half of one coil of the spring, and consider what effects it feels when the spring is being loaded with a load. And in this case, this is a compression spring, but the same rules apply had it been a tension spring. If it were a tension spring, instead of the ends being ground flat like this, there would be some sort of a hook crafted from the wire, and you would apply tension. And the principles are all the same, whether it be compression or tension. So now back to that half of one turn, or half of one coil. Here it is shown in a side view. So there we've sectioned through the one, there's the one cut, there's the other cut, and we say now if one end is fixed, so we're going to fix this end, that's what those little symbols indicate, and we apply the load P, as we know it's in the center of the spring along the axis, and a load P applied at the end of a lever fixed to the other end, the wire may be assumed to be in pure torsion. It may then be considered to behave like a shaft subjected to a torque. Now remember, we did shafts just a little while ago where we considered the torque in a shaft. So we're going to liken the action in the spring wire to that shaft. So if force P is applied at the center of the spring and it is resisting over here, that's where it is fixed, we would then have force P multiplied by a moment arm of D over 2, half of the mean coil diameter. And that would be giving us a twisting effect in the spring steel wire at this cross section over here. A couple of variables that we use often. Capital D is mean coil diameter from the center of the one wire on this side to the center of the wire on the other side would be capital D. Lowercase d is the wire diameter itself. N, lowercase n, is the number of coils. That is how many times the spring was wound around when it was manufactured. And capital P is the axial load, be it tension or compression. And finally, x, lowercase x, is the axial deflection. That is the change in length. In our example over here, let's say we had taken the spring from the free condition to this condition over here. The change in length would be 54.79 minus 41.08. So that would be lowercase x in our case. So back to the wire. The torque in the wire we said was force times arm, which would be force P times d over 2. And then if we think back to shafts in torsion, we had a formula that said torque applied to a shaft is pi over 16 diameter cubed times the shear stress induced. So now where torque was, we put P d over 2, there it is there, and we equate that to pi over 16 d cubed tau, and we end up with this situation over here, and that is a nice formula that's going to tell us the shear stress in the spring steel wire when a force P is applied to a spring, and there are the other variables that we know already, capital D and lowercase d. And then if we look at axial deflection versus angle of twist along the wire, and we look at this little triangle over here, and we actually consider it as a sector, and we take the angle theta times the length d over 2, we would get this little distance over here. It's actually a curved distance, but it'll be close enough for our case. So approximately we can say that x is equal to theta d over 2. Theta obviously having to be in radians. Then we go back to our shaft formulae, and we can get to equate all of this to all of this from the above, and we can conclude that x, which is your spring deflection, is equal to 8 pd cubed n over d4g. So there's our second spring formula that we're going to use, the one for deflection. Now in most cases in an engineering application, the purpose of a spring is actually to store energy for a short period of time or a long period of time. But the point is, we squeeze or stretch the spring, it retains a certain amount of energy, which is then available for use later to perform some sort of operation. For example, to open a door. You squeeze the spring slightly shorter, and it stays there for weeks on end. When you want to open the door, whatever the device is, and you want it to spring open, that spring then releases that energy and performs a little operation for you. Now we'll get to this graph later on, which is P versus X, load versus deflection, but just for right now we need to remember that it is going to be a linear relationship between load and deflection. If you think back to the pictures of the spring in the vise, when there was no load, when P was 0, there was also no deflection. And linearly, as you increase the load on the spring, you get a corresponding linear increase in deflection, either shortening in the case of a compression spring or lengthening in the case of a tension spring. Now this matter of stored energy comes from the fact that we have a triangular area under the graph. So it is half px, because the area of a triangle is half base times height, and that is where this half px comes from. It's the fact that we are dealing with a triangle. So while we're on that, the energy stored in a spring is half px, but x, if you want to relate it back to the spring's dimensions, you can use the formula for x, which was done moments ago, and we can rearrange and actually get U, the strain energy or the stored energy in the spring, to be all of that over there. And there's even a formula which relates it back to the volume of the spring wire, if should you need that, and you can have a look through that to see how we get to that. Now we get to the all-important matter of stiffness. A spring possesses a certain stiffness, and that stiffness lives with the spring regardless of what load it is at. Anywhere between 0 and solid length, that spring will display the same stiffness at all times. And stiffness is denoted by the lowercase letter k, and it is equal to load over deflection. So whatever load you know, as long as you know the corresponding deflection, you can get stiffness. So again, you can rewrite that by replacing P and X with appropriate other formulae. For example, X, we have a formula for that done previously, so we could write it in that format. But importantly, it is P over X, and we'll see later that it can also be change in P over change in X if you are relating two different positions on your graph. It doesn't have to just be a specific load over a specific deflection. You can look at change from one point, for example, to another point on the graph. So there's two ways of looking at it. Now we already know what solid length is from the pictures I showed you earlier. This is the height of a spring when all its coils are touching. Okay, and it would be, if you think about it, the number of coils times the wire diameter, because they are stacked up on top of each other, touching each other. So the length now simply becomes how many we have times the wire diameter. Wire diameter, there they all are. And multiplied by how many there are will give you a formula of ND. Proof load is the maximum load a spring can carry without permanent deformation occurring, without it being damaged. And proof stress is the corresponding stress at proof load. And a final term, proof resilience, is the strain energy. Remember what energy was? The number of joules of energy stored in the spring. And the proof resilience is the strain energy stored when a spring is subjected to its proof load. So when it's at its maximum load that you can use it at, whatever energy is stored is the proof resilience. Here's our first example to kick off with. It says a close-coiled helical spring has a mean coil diameter 8 times its wire diameter. Okay, so remember the mean coil diameter was capital D. That is simply 8 times whatever the wire diameter is. And they tell us that the spring stores 60 joules of energy when it is at a deflection of 36 millimeters. And then also the maximum allowable shear stress is 260 megapascals. We'll probably use that a bit later on. Firstly, determine the load on the spring when the deflection is 36 millimeters. So what we know is when there is 60 joules of energy stored, the deflection is 36 millimeters. So because U equals half px, we can solve for the corresponding load at 3.33 kilonewtons. Next is spring stiffness. Now we know that lowercase k is P over X, and we know that at 3.33 kilonewtons we had 36 millimeters of deflection. So there's our stiffness expressed in kilonewtons per meter. Right, so far all we know is, or all we've worked with so far is energy and stiffness, and we have not designed the spring yet. We still don't know its dimensions. What we do know is that we can't exceed 260 megapascals. So if the spring wire is too small, we might well exceed 260 megapascals under the conditions already given over here. So let's work back and see what size wire diameter we need to not exceed the allowable stress. So we have 260 megapascals is equal to 8 PD over pi d cubed, and we can solve for mean coil diameter and hence wire diameter. So now we have the dimensions of the spring to allow it to do all of the above, including not exceed that stress. What we don't know so far dimensionally on the spring is how many coils it should have. Now interestingly, that affects a number of things, and in particular deflection will be dependent on the number of coils. Now we know the deflection was 36 millimeters, and we also know the mean coil diameter and the wire diameter at this stage. But what's missing is how many coils to wind when we make the spring. And this formula allows us to solve for little n, and it says 3.32 coils are required to achieve all of the above. So now we have dealt with energy, we've dealt with stiffness, we've satisfied the stress issue, and we've also told the person manufacturing the spring effectively how many coils to wind, how to space them out when he makes that helix. Now the second example relates to a spring that is loaded in a fashion similar to this. The question will have thicker plates, but for the purpose of illustration this will be fine. Here we have that very same spring earlier with a threaded rod through it and a washer at each side, which can just as well be a steel plate that doesn't need to be round, and then a nut or a bolt head on the other side. and by advancing the nut along the thread, obviously we are shortening the distance between these two plates or washers, thereby loading the spring more and more as we add turns to this nut. So that is how number 2 is going to be handled. So once again we have a close coiled helical spring, and they give us the specifications: number of coils, free length, mean coil diameter and the wire diameter, and then the properties of the steel, E and G. And we have an 18mm plate now placed over each end of the spring, a bit like those washers in the pictures, and a 25mm bolt passed through. Now that means 25 diameter. Remember, that is to the outside of the threads. The nut being tightened until the coils of the spring just touch. Remember what happens when the coils touch? That is called solid length. Determine A, the shear stress in the spring, B, the tensile stress in the bolt, and C, the extension of the bolt, how much the bolt stretches. So first thing is, we are going from free to solid length, and solid length turns out to be 600mm, and we started with a free of 700, which means that we are deflecting the spring by 100mm. In other words, it's getting 100mm shorter. So just as it reaches solid length, it will have deflected or changed length by 0.1 meters. And there's our formula for deflection, and from it we can find the load that did that, and then the stress that was induced under those conditions. Next is to work out the stress in the bolt, which is under pure tension, so it's simply load over area. Now what's not strictly true here is the fact that we're using 25mm for the bolt diameter. Now remember, a bolt of 25mm diameter is 25 diameter to the outside of the unthreaded portion, would be diameter 25, and it is also diameter 25 to the outside of the threads. And if it's a metric bolt, that would be referred to as an M25, which would be a very non-standard size, by the way. But anyway, for our calculation, what we really should be using is the diameter across the root, because that's where it is experiencing the stress. So this is not strictly true. We don't have that diameter in this case. So for purpose of illustration, we'll just continue with what we've got here and use the 25 diameter. That's over here. But remember, if you do have the ability to work out the root diameter, that would be more accurate. But assuming it was 25, we would have 47.75 megapascals of tensile stress in the bolt. And then if you look back and find the extension formula, we did that in a previous chapter, we can find that the bolt would elongate by that many meters using the extension formula. Now from here on there's a lot of repetition, so I'm not going to go through every example. So what I propose is look at example 3, there it is on the screen right now, and pause the video and attempt it as usual, and only look at the solution once you have made a good attempt at it. First criteria was the shear stress not allowed to go over 200 megapascals, so it's going to determine most of the dimensions, namely coil diameter and wire diameter. So from the stress formula you can get at least the mean coil diameter in terms of the wire diameter. Importantly, we also limited to a solid length of 105 millimeters, which means that we can look at ND at 0.105, which via the stiffness formula can get us a relationship between little d and capital D, and then simultaneously from equations A and B we can find wire diameter. And I'm sure there's other approaches that would have yielded the same answer here. Number of coils is now a simple matter because of the solid length issue, so 9 coils is what we have to use if that is to be the wire diameter. Next is the actual deflection at the maximum allowable stress. Well, let's find the load and hence the deflection at 0.038 meters. Next is the tutorial, which is 2 questions. Stop the video as usual here and work through those. Hopefully number 1 looks something like that, nothing too complicated there. nothing we haven't done before. Likewise with the second one. Now this additional tutorial is taken from a design set of notes, so it all uses the same principles, but there might be a bit more of a leaning towards design aspects, for example standard wire sizes, etc. So you can also start by working through those. In the first one we must find the load that would cause a shear stress of 345 megapascals in the spring with those dimensions. So nothing complicated there, we can immediately just put in the dimensions into the stress formula and find the load that caused it. And these notes used Y for deflection. You can just change that to lowercase x because that's how we set out the formula at the beginning. So deflection is 8pd cubed n over d4g. Again, we have all the dimensions and we can find what the deflection is. The second one is really a repeat of the first one. Again, we have dimensions and a required stiffness, and we must find the diameter of the wire, mean coil diameter, and the number of coils required. And there's the load and the stress and the modulus of rigidity. Now also from a design perspective, you've got to look at what variables are not negotiable and which variables are negotiable, because sometimes you have to round things off or select an available size material. Okay, now in this case it says is to have a stiffness of this much and a solid length of 42 millimeters. So those two sound like they are not negotiable. Whatever machine requires the spring cannot deviate from those two variables. So we've put an asterisk against the two that are not negotiable, stiffness and solid length. So we must find a suitable wire diameter. So solid length formula gives us the relationship between number of coils and wire diameter. Again, just be careful, the capital N, we were using a lowercase n up till now, you can change that. Stiffness formula, stiffness relating to dimensions, that's its formula. And the stiffness we wanted to be a certain value, which was 0.8 kilonewtons per meter. So in it goes into the formula, and we can get little d in terms of big D. And then we also know that shear stress is 8pd over pi d cubed. So again we can get d in terms of d, which is good news because then we can have a simultaneous equation as follows. And from it we can find the ideal wire diameter at 4.292 millimeters. Now comes the design angle here. We don't have it in front of us, but if you were out there in the design world, you would now phone around or inquire or look on the internet to see what wire diameters were available to you, because obviously it would not be financially viable to have a wire of exactly 4.292 made for you, because there would be vast cost. But if you look up on the table and you find that the closest wire available to you is 4.5, and that's all that you can use, you have to now update your design and change certain parameters to now accommodate this new size and still not change your not negotiables, which were stiffness and solid length. So what we do is we update the stiffness formula with the new wire diameter that we are forced to use, and we find that to accommodate our solid length of 42 millimeters, which was not negotiable, remember, we must have 9.33 turns of this new 4.5 millimeter wire. And finally we'll have to change the mean coil diameter to 70 millimeters to accommodate all of this. Okay, let's look at the third one. A rod of 3 millimeter diameter is coiled into a tension spring of 20 turns, effective mean radius of 25 millimeters. Remember, double that to get diameter, mean coil diameter. Determine the stress due to a 12 Newton load, elongation produced, stress which will be produced by this load, and the elongation of the spring were given an initial compression of 4 newtons between the coils. Okay, so this is a tension spring, but it starts with 4 newtons of compression. For whatever reason, they've first preloaded it with compression. Then you apply the 12 newtons. So you'd first undo the 4 newtons of compression, and you'd end up with 8 newtons of tension, actual tension in the spring. and finally the frequency of oscillation. So we start with stress versus load. So knowing all of that information, we can find the stress in the wire. You'll have an X over here for deflection, so that is the deflection under those conditions. And then for the C part, the actual load was 8 newtons, as we discussed earlier, and we find that extension will be 24 and a bit millimeters. Then you can work out the stiffness using the stiffness to dimensions formula. And then finally the frequency of oscillation of the spring when a mass of 0.6 kilograms is hung from it. Go back to chapter 14 and have a look at the formula that we gave you over there, and you can find 3.74 Hertz frequency of oscillation. Right, to finish off this tutorial, I'd like you to look at 7, 8 and 9. There they are over there. Stop the video as usual, and you can have a look at the solutions once you've tried all 3 of those. Okay, to finish off with, let's do one from your textbooks, page 117, one of the few spring examples in that book. But they say a coil spring which compresses 1 millimeter for every 14 newtons applied to it, that is indicating stiffness, has a free length of 125 millimeters. You know what that is. Determine the work done in compressing the spring from a length of 100 to a length of 50. So from some arbitrary length, which is shorter than the free length, to another arbitrary length of 50 millimeters. So there's 3 sketches of the spring in 3 conditions. First, free, when there is no load, and then a length of 100, and then a length of 50. And we need to know what happens from here to here. Stiffness we can find because we were told that the spring compresses 1 millimeter for every 14 newtons, so that's not a problem, so we can find the stiffness. And we can then also plot the force extension graph. Now remember that springs have a straight line graph, and it starts at the origin, because with no force there's also no extension, and as you apply more and more force, so this graph climbs. Now incidentally, the slope of this graph is in fact 14,000, so you can remember that the slope of a stiffness, the slope of a force extension graph is in fact the stiffness, if you can use that somewhere. In our case, we've got to find the work done in going from this condition to this condition, which on our graph would be some point over here to some point over there. So in essence, what we need to find is the area under the graph in that zone there, which consists of a triangle upon a rectangle. And if you look at all the values, you can add the 2 together. There is the triangular area and there is the rectangular area, and you'll find 35 joules of energy was input to get the spring from here to here. When it was here, the total energy possessed by it or stored in it was greater than that, but that's not what was asked for. What was asked for was the energy to go from this position to that position.